Welcome to lecture 26. Today we are going to talk about the generating functional. We will construct the generating functional much like in the spirit of Gaussian integrals. So if you remember when we did the Gaussian integral with prefactor a over there, so exponential minus half ax square, and if I took derivative with respect to a, then I got the 2-point gains function, 4-point gains, second moment, fourth moment, and so on. So this was done by introducing the derivative under the sign of integral. That's the Feynman's trick. So similar thing we'll do over here, and it's done in many branches of mathematics, where you construct a function whereby taking derivative with regard to some of the parameters or some of the variables in the function, you keep on generating the desired result. Since here we require to take derivatives, we begin our discussion over here with the functional derivatives. Okay, so when we take derivatives in the discrete case, discrete means when we have a countable many variables with regard to which we are taking the derivative, so then we can just have the first very simple rule is that del by del xi of xj is 0 unless I equal to j, so that is just delta ij. Okay, now this particular relation in the continuum case becomes like this. So I have delta derivative del of jx. I'm taking derivative with regard to this jx of a function jy. So this would the corresponding thing of delta ij in the continuum limit is a 4-dimensional delta function of x minus y. So when x is equal to y, then this derivative exists, otherwise it's 0. But since it's happening in the zero measure thing, that's why this delta function is there. Now other things that we have is del by del xi of this summation over kj xj. So I can just simply use this rule, take this derivative inside the summation, and when I use this rule, then I get kj and delta ij, and when I sum over j, then it just becomes ki. Okay. So similarly here, if I take derivative of del by del x jx of, now here the summation over j becomes the integral over y of jy phi y, and again I bring this derivative inside the sign of integral, and when I take derivative of jy, I get delta for x minus y, and uses d for x to integrate the delta function, you get phi of x. Okay, so basically this is the basic rule how we do the derivations, and then everything else is built from there. For example, this del by del x of exponential I, this d for y jy x phi of x y, phi of y. If I take the derivative of this, then first thing I do, take the derivative of the exponential with regard to exponent. So that will just give me the exponential again written over here, and then take the derivative of the exponent with regard to jx, and using this rule over here, it just gets I phi x I, because this I factor was there. Okay. So here nothing different coming up over here. A new thing that comes is given over here is del by del jx of integral d for y. Now j is appearing not as it is, but derivative del mu of jy is coming contracted with v mu of y. When I do this derivative, okay, when the derivative of j is involved and I have to take function derivative with regard to j, then what I do, first thing that I free up j by doing what's called integration by parts. When I do that, this derivative mu start acting on this, and I'll get the minus sign over there plus the boundary term, and then I take derivative with regard to y using this delta x minus y, and then integrate over d for x to get rid of delta, and what I get is minus del mu v mu x. Okay, so here integration by part is performed. It's very easy to check a discrete version of this also. It's very illuminating how you get you can write this in the discrete version, and you can figure out, maybe in the homework you will do that. Okay, write this thing in a discrete version, and you will see how using something simple rule like this guy over here, negative of derivative appears naturally over here. Okay, so this is how we'll perform the functional derivative. These are simple rules. Now let's go on to define what's called generating function. So let's first define z0 of j is equal to this d phi, the path integral exponential I minus t to t d4x and the Lagrangian plus j times phi. Okay, so it was everything as it is except this j times phi, jx times phi x is introduced. This is called the source term, and here the Lagrangian for the free theory is there. We are using, okay, just a quadratic part. That's why the z has a 0 sub label over there. 0 is a subscript because I want to emphasize that we are talking about the free theory, not the full interacting theory. Okay. So clearly, if I put j equal to 0, okay, that is nothing but this z0 0, which is phi b exponential I h 2t phi a. That particular integral corresponds to this guy. This is the denominator for all correlation functions in the free theory. Okay. This is the thing that with which we have to divide, as we discussed in the previous lecture 25. We saw that how 2-point or 4-point Green's function has this 1 over z0 over there as a denominator. Okay. Now once we have this, clearly if I take derivative with regard to jx, so here I already seen that how the derivative with regard to jx appears is I times phi x appears. I want phi, not I times phi, so what I do, I multiply by minus I to get rid of this I over here. That is exactly done over here. So minus I del by del j x1 of z0 j. If I do this integral, then I do this derivative. Okay, so this is a z0 j, and I perform this derivative. Then here, because this is the only piece which depends upon j, if you take derivative, minus I times phi, which means just phi of x1 will appear over here, and this exponential sits as it is, and so on. You can take many derivatives. So let this be repeat this kind of derivatives, minus I del by del j twice. Okay, and if I do this twice, and then I will have this d phi, then phi of x1, phi of x2 corresponding to j of x1, j of x2, and this function. Then what I do, I put j equal to 0. This is gone. After taking the derivative, I take j equal to 0 and then divided by z0 0, and that is nothing but my 2-point correlation function. Okay. So in a way, z0 is the generating function of n-point correlation function in the free theory. Sorry, not Dirac theory. This is free client coordinate theory I have. Okay, so let me just remove the free theory part. Just free theory. Okay, so let's proceed from here. This is a free theory. Apologies for the delay. Okay, so if I have to look carefully again and try to evaluate this z0 of j, idea is, can I evaluate this? And in the lecture 24, when we talked about the mathematics part of this, we actually considered this guy. We have exactly this kind of stuff, but we wrote here not in this way, but we wrote in terms of operator. So this is what we have: d phi exponential I d4x, and here integration by parts has been considered to convert this del mu phi into phi times minus del square phi. Okay, so it is phi times minus del square minus m square phi, and this basically is my operator a plus j phi. So if I have this kind of integral, we know how to invert it. Rather write the result in terms of inverse of a. Now inverse of a is defined using the a acting on some dxy is just the delta function. Okay, so actually for the Green's function for the kg equation is written like this: so del square plus m square acting on d of x minus y is minus I times delta for x minus I. So this is how the Green's function is defined. Okay, this is here. difference function is defined in such a manner. So now what I am doing over here is to take multiply the whole thing by minus 1, so that get rid of this I over here to make this operator into A. Okay, so here I is only sitting there, then I multiply this by minus I, which is here. Okay, to make the right hand side equal to 1. So this becomes A, and whatever remains over here to make the right hand side as delta function is A inverse. Okay, so I have A inverse is minus I dx minus y. Please contrast this with the lecture 24, where the A inverse was nothing but dx minus y. Okay, so in the formula over there, if I replace dx minus y with minus I times dx minus y, then this is what I will get. Z0 of j is Z0 0 times exponential minus half, no I sitting here, d4x d4y jy dx minus y j x. Okay, and that I intend to write symbolically, since I'm going to write this thing many times. I write z0 0 exponential minus half jx dxy jy. So here repeated coordinates are integrated over, jy and the y is integrated out and x is integrated out. It's like the two indices of the matrices summed over in the discrete case. Okay, so this is the Z0 thing. The first actually in the lecture 24 we just said that Z0j is proportional to this. We did not say what was the proportionality constant, and that you can see that that was nothing but, if I put j equal to 0, this becomes 1, and that is my proportionality constant when when j equal to 0. Okay, this factor will be nothing but 1. So for non-zero j, this is the expression z0 0 is my Gaussian integral, pure Gaussian integral without shift and all those things, and this is the overall factor from the shift of phi. So this is a shift in phi that we have to perform in this line over here to complete the square, and this is extra pieces that will hang around. Okay, and now once I have this z0 of j as a function of j over here, so now I can obtain endpoint correlation function by multiple functional derivative with regard to jxi. Okay, so all I have to do is keep on taking derivative of this function, and this is pretty simple looking function whose derivative we have to compute. So let's look at this. Okay, so del by del jx1 of z0j, okay, would be, if I take the derivative over here, so this is my z0j. So what happens, and this is clearly independent of j, so I'll take the derivative over here. So first, derivative of the exponential with respect to exponent will just repeat the exponential again, so this factor will come again, which I just write z0j, and then the derivative of the exponent, which is written over here. So this is equals z0j, and if you take the derivative of the exponent, so first jx will act on, you take derivative of jx here, the left side guy, sorry, right side guy, so it will give me jx dx x1. Okay, and using the delta function for that and integrating out one of the thing. So now you see here two indices were repeated, two coordinates are x and y are repeated. That means this is nothing but this, the full double 4-dimensional integral. Now here one derivative and one delta function, one derivative brings one delta function and one of the integral disappears, so it becomes one integral still. The integral d4x is still alive over here in this expression. Okay. So we take the derivative acted on jy over here, and now if when it acts on jx, I get this particular guy dx1 y jy. Okay, now what happens that this dxy is a symmetric function. So basically this piece and this piece are nothing but the same, because only difference is the name of the dummy variable, which is integrated out. Okay, so I'll just sum them up and write that the derivative of my partition function or generating function, you can say z0j with regard to j of x1 is just z0j minus dx1y jy. So jx1, x1 is sitting here as a free index, and the free index appears over here. Repeated index, as you can see, is integrated out, repeated coordinate. Okay, so this is my rule. Now I have to compute the 2-point function. So the numerator with full the j dependence can be written as following. So here we can see that I have to take derivative. This we have seen earlier. Here I have to take derivative of minus I del by del j to get the twice to get the 2-point correlation function, and then divide by z0j. So what I do is the numerator has these two derivatives. So this minus I times minus I is nothing but minus 1 times del by del jx2 times del z0 by jx1. So I replace this by the expression that I have over here. Okay, so there's one minus sign over here because of this definition of i's, and one minus sign from the derivative that I have. So these two cancel. Okay, and now derivative of this whatever in the bracket without the minus sign with jx2 when I compute. So once the derivative will act on this piece, and once the derivative will act on j0. So when a derivative acts on the second piece, okay, so note that jy will disappear, and again before y and delta function will take care of all this extra integrals, and so here they are non-integrals. So it will be z0j dx1 x2. Okay, that propagator came out. But when I act this derivative on z0 of j, it will bring down again this kind of factor. Okay, so it is z0j minus dx2, because I'm taking derivative with regard to x2, for some z jz. So here z is integrated out, and here y is integrated out. Okay, so here is like two 4-dimensional integrals are there. Now, so this is the numerator I got. Now to find this guy, I have to 2-point correlation function. I have to have 1 by z0, and numerator evaluated j equal to 0. When I take j equal to 0, this piece disappears, and z0j becomes z0, z0 0. That basically cancels out from here, and I have just dx1 x2, or in other words dx1 minus x2. Okay. So this is very trivially I got the exact propagator over here. Okay, so this is supposed to be a propagator satisfying all the conditions that I wanted it to satisfy, and this is dx1 x2, x1 minus x2. Now we already saw we discussed that if I do a third derivative, then well, 3-point Green's function will be all 0, but here I have to confirm that using functional derivative method. So although I'll compute the numerator of the 4-point Green's function, but to compute the 4 derivatives, I do have to go through 3 derivatives, right? So we'll see how it happens. So for each field, I have to have minus I del by del j, and there are 4 of del minus i's, giving me overall factor 1. So it's del by del jx1, del by del jx2, del by del jx3, del by del jx4, acting on z0 of j, I should have said. And of course this derivative with regard to 3 and 4 written explicitly, and derivative with regard to 1 and 2, we just take this expression from here. This expression I will copy inside. Okay, so this is my starting point. I recycle my previous result, and then I act by del jx3. Now when it is acting on the first, so there are 2 terms, so here j appears only here. When it acts upon this, it returns me z0j with a minus sign, which kills this minus sign, dx3y jy. Okay, here y is integrated out, and dx1 x2. There are 2 propagators and 1 j sitting over there. Now let's act this j3 over here. So first let me act on this term. So it gives me z0 as it is, and dx2 x3, because I'm taking derivative over to jx3. This term will give this, and this term will sit as it is over here. So this is one of the term, and when the derivative acts on this guy, I get this this propagator, but this term sits exactly over there. Now third possibility is when j derivative acts on z0j, then it brings with a minus sign z0j, x3x jx, zx2 z, zz, zx1 y, jy. Okay, so you have three different integrals are there. Now here, this is the numerator. Okay, so this is the numerator in the guy sitting inside the bracket is the numerator for the 3-point Green's function. If I put j equal to 0, that gives me 0. So 3-point Green's function will be 0 because everything is proportional to j. Here one factor of j is there, here one factor of j is there, here's one factor of j, and there are three factors of j. In fact, we'll see this is the kind of pattern that for all the odd guys, there will be one factor of j, three factor of j, five factor of j, and so on, depending on how many point Green's function at what order you have computed. For even point Green's function, there will be 0j, 2j, 4j, and so on. Okay, so when I put j equal to 0, only the 0j's will contribute. Now let's perform another integral, and after derivative, and after plotting the derivative results, each term has z0 in it. That's why the z0 is written separately. Ideally, we should write with each of these terms so that we don't make a mistake for the next level of derivative. Okay, so when this x4 acts on the first term over here, okay, so what it gives me del j, because it can act on either z or this guy. So when it acts on this guy, then it gives me two propagators. So this two propagator is written over here, and z0j, which is written outside. And when it acts on z0j, then it brings another factor of dx4w jw. It brings additional factor over here, and this was what earlier already in. So basically, derivative of this piece is these two terms over here, and when I take derivative of this guy, again a derivative can act either here or here, and this is this term over here and this term over here. Okay, so one guy will just give when just the two propagator times zc, which is written in the first line, and second time it will bring another factor of j than what it was already there, so it becomes two factors of j with a minus sign. Then same here, same kind of thing repeated here. So the product of two derivatives are written over here, and the additional piece is over here. Okay. So this is about these three terms. Now when the j acts on this guy, so we just say 1, 2, 3, 4. Using the Leibniz rule, it will give me 4 pieces. So when it acts on any one of these, the derivative, it will just reduce derivative by 1 and makes it 2 derivative piece. So this is here, it gives me, when it acted upon this guy, it gave this term. Okay, dx3 x2 is there. It acted upon this term, it gave me the second piece over here, and when it acted upon the third guy, it gave me this third piece over here. Okay, and when it acted upon zz, it brought down one more term. Okay, and just to remind that this is the most complicated term here that I'm writing, has 1, 2, 3, and 4. So w, x, z, and y all are integrated out. So this particular thing is actually expression is d4x, d4y, d4z, d4w, dx1 minus y, jy, dx2 minus z, jz, and dx3 minus x, jx, and dx4 minus w, jw. It is this long expression is written in a compact manner over here. Okay, here there are two integrals. Okay. Now clearly, if I put j equal to 0, all the terms in the second, third, and fourth line go to 0. Only the top line is non-zero. Okay, and then this z0j becomes j becomes 0. So it also, I have to divide by that factor to get my 4-point function. So my 4-point function is the sum of three terms. Each one is a particular pairing, corresponds to a particular pairing. So I have four functions for 4 points x1, x2, x3, x4, and I have to create pairs. So this can be done in three ways. Okay, so x1 connects to x2, the last two has to connect. x1 connects to x3, the other two has to connect, and x1 connects to x4, and the rest two has to connect. There are three ways. Like the 4-point function, if I go for the 5-point function, I take starting from here, and z0j should be with each term, and then I take derivative to get the 5-point function. So here in the first three terms, the derivative will act on z0j and will create a j dependent piece. In these terms, when z derivative acts on z0j, it will create another piece. Okay, so the first line will give me a term with 1j, the second line and the third line, and the one term in fourth line, all of them which has 2j with z0j. That will give me, when the derivative acts on zj, it give me a term with 3j's. Otherwise, when the derivative acts on one of the two these j's, then it will give me a term with single j. So basically, I will have several terms with single j in it and several terms with triple j in it. Okay, and when you look at this guy, there will be a term with 5 j's in it, and there will be terms with 3 j's in it. If I take derivative of this multiplied by this. Okay, but whatever we get, there will be no term which is independent of j. So when you put j equal to 0, the entire thing will go to 0. Okay, and when it comes to 6-point function, well, we have to start from there and then take another derivative. Okay, and that is part of your homework. You have to systematically write this thing. And so 6-point function will have x1, x2, x3, x4, x5, and x6. And there, the way to combine is that you combine x1 with any one of them. So there are 5 ways to combine. So once you pair them, there are 4 more are left, and they, given 4, they can combine in 3 ways. So 5 times 3, you should have 15 terms in the 6-point Green's function. Okay, and so on. So the point here is that all these things we could have obtained, like this 4-point Green's function, we have already seen using the canonical approach. Okay, where using the Wick's theorem on all possible contraction, we got that. Here, we don't have to worry about the permutations and combinations. All we have to do is that make sure you take the derivatives carefully and don't miss a term, and you'll generate all possible terms that should be there in the correlation function. Of course, you'll generate far many more terms, and when j go to 0, they all go to 0. So if you are smart enough, you know exactly which ones to throw away. For example, here's a 2-point Green's function. I have already taken 2 derivatives and 2 more to go. So I have to make a call, okay, here, that can I simplify and throw away some terms? Idea is no, here there is no j hanging around outside. That setting j equal to 0 will give me 0. So only way this will contribute after 2 derivatives is that when derivatives act on z of j. Okay, at least one acts here, and then the second one acts when the new j is created. Okay, so I cannot throw this term away, and likewise here I cannot throw this term away because both derivatives can act on this z of j over here, j and j term over jz, jy over there. So I can't throw away this term. Okay, so let's proceed. So I did one derivative and I got this term. One more derivative to go. Okay, now let's look carefully. This guy has 1j sitting outside, okay, which can be taken down by this derivative. Okay, so this will contribute. Okay, wherever there is one j is there, it will contribute after one derivative. Okay, but when derivative acts on z of z0 of j, that will not contribute. But okay, I can't throw away this term, but I can throw away this term right away. Why? Because it already have 3 j's. Okay, if I take one derivative, one of them will be down, 2 of them hanging around. When I put j equal to 0, this is gone. So it is sufficient to compute the things from the first 3 terms, which is this first 2 lines. The last computation I don't have to do if I'm doing 4-point Green's function. Okay, but if I'm doing 5-point Green's function, or say I'm doing 6-point Green's function, so apart from this, I have 2 more derivatives to compute. Okay, so this is 3 derivatives already done, and say 3 more to go, then I can't throw away this term. if I have to compute the 6-point Green's function. Okay, but let's say I did the 4-point Green's function, 4 derivatives already I did, and to compute 6-point Green's function, I still have to do 2 more derivatives. So 2 more derivatives means all the terms with 2 j's are to be included, but this guy already have 4 j's, so only 2 more derivatives to go. Of course, this will not contribute, so I can throw away this piece right here when I'm going to compute 6-point function. So I need to know my goal, and then intermediate steps I can just throw away certain terms. In fact, in all the pieces where 2 j's are there already there, the derivatives better act on this, because if the derivative acts on z0 of j, it will create another j, and that particular piece will also go to 0 when j goes to 0. Okay, for the 6-point Green function. So I am interested only on those terms here where both the derivatives act on this j's. And for the first line, when there is no j's hanging around, both the derivatives must act on z0 of j. Okay, so this is how we'll have not both the derivatives. One derivative will act here, and then one derivative will act on result of it, which is like actually acting both derivatives on this guy. Okay, so one has to, so this is what I wanted to show over here, is that using the functional derivative method, one can have this nice generating functional, and we can create any Green's function by carefully taking derivatives. In fact, since here rule is pretty simple for derivative, and I can just say here that this is the rule, this is equal to this, this is, you can take it as a rule. Okay, and second rule is which is the very first place it is given, where you take this one. Okay, so this is just jx and y, so instead of jx there will be dx dxy j 5y. Okay, and then you take derivative with regard to, sorry, jy, so derivative, and then just the propagator will sit. So a certain version of this integral, and this are only 2 things you need to apply repetitively to find any Green's function. So it is so simple that one can actually automate this using some simple code also. Okay, anyways, I want to see full detailed computation with a 6-point function. You can actually start from here and get to the 6-point function. So with this, I conclude the lecture on functional derivatives. This is where we dealt with the scalar and how path integral can give me a lot of propagators, a lot of Green's function in a scalar theory. Right now we are talking about only the free scalar theory. Next lecture will be about how do we deal with the fermions, and there we will have to introduce some anti-commuting numbers to copy the behavior of the anti-commutators of fermion operators. And afterwards we'll have case theory, and then we'll go on to interacting field theory and how to extend this functional derivative method for the interacting field theory. Okay, because we want all this Green's function in the interacting theory. Right now all the all the propagators, if you see, they are all just, the whole term is just bunch of propagators, and there is no point, no interaction point over here where all the points meet. So we'll discuss that later. So for the time being, this is all.